In this presentation, I'm going to talk about scene graph generation from images. And first of all, I'm going to introduce the problem of scene graph generation. And then I would like to talk about a few approaches to one of the main challenges in this area, which is called compositional generalization. Okay, so what is scene graph generation? It is the problem when we have an image as the input, and we want to predict a scene graph, which is a collection of objects and relationships between them. So the task is to use some model F that will predict the scene graph from the image, and it has many different applications, starting from I think the most important one, visual question answering, VQA, and there are also image retrieval, caption generation, and many other applications. So the idea is usually that scene graphs allow you to work in the semantic space, so it's much more harder, for example, for visual question answering, it's much more harder to directly predict the answer given some question and image, to directly predict the answer from the image without explicitly predicting objects and relationships between them. So in contrast, once you first predict the scene graph, then it's much easier to predict the answer from this semantic form. Okay, so another important definition in this problem that is often used is a triplet, which is a set of objects. So it's a tuple of object, predicate, and another object. For example, bear wearing helmet is a triplet, and ZS triplet means it's a zero-shot triplet. So these combinations of objects and relationships has been never observed in training. And for example, this triplet, bear has arm, has been observed during training. It's typically a very frequent relationship because usually bears have arms, but usually bears don't wear helmets. So that makes it much harder to recognize bear wearing helmet, like all of the three concepts correctly. So usually the model will struggle to classify either the bear or the edge or another object, because this combination was never observed during training. Okay, so usually the approach to tackle this problem boil down to a simple pipeline, which is sometimes complicated too much in the papers, but essentially this can be represented as a more simple version as I show here. Basically we have an image, and the main work is done during object prediction, object detection, and construction of edge, of node and edge features. So once you have a very strong detector, such as FASTER or MASCAR CNN, then the problem becomes much easier because the features will be node and edge features will be very good. So node features correspond to the features of objects. Usually they are obtained by average pooling of convolutional feature maps, and edge features are obtained in the same way but for the union of bounded boxes. So given two detected objects, for example, this yellow small box and maybe this blue box, then you compute the union of bounded boxes, and you extract the same way you compute the you perform average pooling of the feature maps to extract the edge feature. So you are gonna have much more edge features because you compute it for all pairs of objects, and then you're given that those two matrices, you can apply some graph-based model, or it can be actually not graph-based, but yeah, it makes sense to use some graph-based model to improve results, and you generate the graph. So I'm gonna describe a little bit later more details, and so there is actually not so much research on applying graph neural networks in this domain, in which case you would have X features as node features, and you would have some trainable parameters W, and then this adjacency matrix would encode the relationships between nodes. So this would be sort of edge features, but usually this adjacency matrix is like float valued, so it's a matrix of values from 0 to 1 or something like that. For example, it can be in this case this adjacency matrix can be built by computing spatial distances between two objects. Okay, so moving forward in more detail, this pipeline can be represented as following. Yeah, so again we have some faster mask RCNN to extract node and edge features, and at this stage we usually have a complete graph because we compute edges for all pairs of objects, because at this stage we don't know if two objects have a relationship or not, so we need to figure out that later, and then we apply some graph-based model. For example, it can be message passing that was used, which is one of the popular methods in literature. You can find a reference in our paper, and so yeah, and then you predict classes and edges for based on these visual features. And so one of the edge classes is the background class, which is shown in red arrow. It denotes the edges that were not annotated by the human. So it can either be because there is actually no relationship between the two objects. For example, probably short and cup do not have a particular relationship. There can be still a spatial relationship, but usually humans do not annotate that, and it can be either because it can be the background edge can be also just because the human decided not to annotate the relationship for some reason, just because it's a human factor, right? And so, and during at test time, once we train such model, we want to predict these background edges so that the resulted graph will be sparse. We don't want to predict a complete graph, because it will be not very useful for downstream tasks such as visual question answer. We want to predict a sparse graph where relationships will be strong. Okay, so this is the notation for the graph, is a set of objects and the relationship, and the task is to predict a graph given an image. Okay. Next is that so to simplify this problem, as I mentioned, people usually apply some object detectors, and yeah, essentially in the probabilistic sense, we just need to solve the problem of predicting objects and relationships. So this problem, predicting a graph given an image, can be very difficult if you want to predict a graph directly from the image, but once you use the detector, you simplify the problem a lot. And sorry, this was cut off below, but yeah, you can find all those formulas in our paper that I showed here. So it introduces this problem in a intuitive way. Okay, for example, this is how the predictions would look like for some image. On top we have ground truth annotations, and you can notice that they can be very, very sparse. So the annotator, and it's also due to pre-processing that often apply to these datasets. So this pre-processing includes removing some rare relationship classes from the dataset to simplify the task. So in the result, many graphs are very sparse, such as shown here, so only one edge. But the model predicts a relatively dense graph. So in this case, I applied some threshold to throw away edges with low confidence. Confidence, I mean the softmax outputs. And this edge is bolded because it actually corresponds to one of the triplets that has never been observed during training. So this is the test image and the test annotation, and this is our prediction. So this is our detections and our predictions for this test image. So evaluation is usually done using a recall metric. So there were some other works that tried to perform evaluation from the graph perspective, but it's not so popular. So usually what people measure is this recall at k, where k is the number of top predictions that you consider. So the larger the k, the better are the results, because you consider more predictions. For example, for this image you have a set of ground truth annotations, which is this set, and then you have a set of predictions by the model. So it can be actually like you can have many more predictions, but I show top 100 because we compute R at 100. So that's why we only concern top 100 predictions sorted by score, which is produced by the multiplication of softmax scores of each object and edge. Okay, so all other triplets have lower score, like the multiplication of their scores is lower than this value. And now, so we have these two sets, and we just compute the intersection of two sets and normalize by the number of ground truth triplets. So the problem with this metric is that it can be dominated by frequent triplets. So, for example, man wearing short is a very frequent triplet that appears almost in all images, and we can simply ignore the image, our detections, and can always predict this triplet, or maybe this triplet as well, cup on table. Like you can choose a bunch of very frequent triplets and always predict them, and you can get a very high score because that's the nature of these data sets. But it will not show you actual performance. Like it will not show you if your model is actually effective, because at test time you can be given an image where the cup is not on the table, but maybe not under the table, but it can be a very different juxtaposition of objects, and so it's sort of it can be out of distribution combination of objects, and the model will most likely fail to recognize them because you just predict the most frequent relationships. So a more interesting metric that actually measures the performance of models more accurately is this zero-shot recall, where you consider like the set of ground truth triplets only includes zero-shot triplets, which in our case I guess would be cup on surfboard, so maybe another triplet. So there will be fewer triplets in that case, and the results will be much lower, but they will be more indicative of the performance. And okay, so there are some very good PyTorch wrappers. I'm not sure about other deep learning frameworks like TensorFlow. There are probably other wrappers for them as well. So I would particularly highlight the first one, which is based on this year's CVPR paper, and there's another wrapper from last year, ICCV, which won some challenges as well, and some older method that is still it's still supported on GitHub, and this is our reference to our paper, our code. So it actually it's very simple. So I tried to make it very simple to use, but the performance can be a bit lower than in those models, in those repos. But it can be much more difficult to make those first three work. But if you do, then you can get better results than in our case. Yeah, and our repo, for example, is based on this older code that was very nice, but no longer supported because it requires you to use PyTorch 0.3, which is very old and not supported by some GPUs. Okay, so the data sets that we have in these tasks are mainly visual genome, that is usually reported by all papers, and the more recent is GQA, that essentially is a clean version of the visual genome, and it has actually a larger vocabulary with more classes, so it's more interesting, more large scale, I would say. Also, there is this synthetic data set that was used in many works, and now I think it's more interesting now to work in the dynamic space where you want to analyze videos and to predict scene graphs for each frame, maybe, or maybe a scene graph representing the entire video clip. So nodes can be more spatial temporal. So there's like very little research in this space. So the main challenges in this problem, in the scene graph generation problem, is first, as I mentioned, is engineering efforts, and yeah, it can be very time consuming just to make it work, and also it would require you quite a lot of compute and running time as well, and the visual genomes, the data sets are getting better thankfully to the GQA, but the original visual genome is quite noisy. And yeah, evaluation metrics, as I mentioned, also are not very nice sometimes. And so there is this very big compositional generalization challenge that I already mentioned, so which includes the ability to recognize novel compositions of objects and relationships, and I also found that the methods that people use, the methods that people use in this area are very complicated sometimes, and it feels unnecessary complicated. So, for example, graph neural networks are not very explored, and this is a very simple method. So I would love to see more research on that topic, on scene graph generation using these graph neural networks. So there are a lot of challenges, but it doesn't mean I would like to outline these challenges not to scare people, but just to say that there are a lot of room for improvement, and applications are interesting. Okay, so also, I would like to briefly talk about two approaches we had. We investigated in this to improve compositional generalization in particular. So one is based on improving the loss function, and another is based on generative models and GANs. So compositional generalization exists not only in scene graphs. It's also known in other topics like image classification, where attributes of objects can create different compositions, and this is orthogonal to scene graphs, but you can find this also interesting. So, for example, this attribute-based representation of images can make it possible to predict classes for unseen, make predictions for unseen classes based on attributes, so which is very interesting. So this compositional generalization is challenging, as I mentioned, because the training distribution contains only a tiny fraction of all possible triplets, and this makes the model very biased towards those frequent relationships, like those cup on table men wearing short, and the model would struggle to correctly recognize like the triplet correctly for if it's if it has never been observed during training. So the examples I show here, Okay, so this this problem is also difficult because on the one hand you would like to use the statistical bias that, for example, cap is always on the table, so you would intuitively assume that it doesn't make sense to predict anything else. Like it doesn't make sense to predict a cap on surfboard if statistically the probability of cap on table is 100% or very close to it. From the statistical point of view, it doesn't make sense to predict a cap on any other object or cap under the surfboard, or sorry, cap under the table, because it was never observed, right? But this makes models very difficult to generalize to out of distribution compositions that the model hasn't seen during training. And it turned out that simpler methods such as message passing are much better in terms of compositional generalization than more fancy and newer methods that exploit this statistical bias. So these models are not so good in compositional generalization, but they would give you a little gain in terms of the evaluation metric, but in terms of compositional generalization metric, it would give you a huge drop actually. So it depends on your application. Either of those choices can be applicable. And yeah, for example, they show that in this paper, Neural Motives paper, they show that the blind model that do not look at the image at all, so it just predicts the most frequent relationship, it outperformed the previous state of the art on this data set. And in our paper we show that in terms of compositional generalization, which is measured by this zero-shot recall, this method, Neural Motives, that relies on this frequency bias, even though it gets better results in terms of the standard metric, so it's doing better than this message passing method. In terms of zero-shot compositional generalization, it does much worse than this older method, so it's almost 3 times worse, or at least 2 times. And in our paper, this one, we show that how to improve results on this compositional generalization for all models, and I'm gonna describe a bit very briefly this approach. So we found that the baseline laws that used to train these models doesn't learn well from large and sparse graphs, and there are a lot of them in the training dataset, so the model essentially ignores half of the training dataset. And by normalizing the laws in a particular way, we show that in our case the results are improving if we increase the size of the graph. So this is the result using small graphs, this is using large graphs, and this is result using all graphs. Whereas in the baseline case, the results are not what we expect. And this is some qualitative results. We just wanted to show that if our model makes mistakes, it makes it in a more reasonable way, because annotations are not perfect, so mistakes can be actually accurate predictions sometimes. So another approach that we considered, it it's described in our another paper. It's based on generative models, and the idea is that we try to perturb scene graphs. So, for example, given some ground truth annotated scene graph, we perturb it using a language model, and we create a new scene graph based on that. So this is, we perturb scene graphs based on BERT in this work, but other language models can be tried. And for example, we mask out some of the object or edge in the triplet, and the BERT can returns plausible candidates for this mask. So we randomly can choose either of those candidates, and we can also add the context to the query to make the possible candidates different depending on the context that we want. So this is done to increase the diversity of perturbations. So we apply a generative adversarial network in this work, and this is the pipeline that can be a little bit complicated, but we describe the details in the paper. So the idea is basically we perturb scene graphs, and this is the generator. It generates visual features, and we want to match the distribution of real visual features of nodes and edges and generated visual features. So we use a discriminator to train this generator, and then those augmented visual features coming from the generator are passed to the model that predicts nodes and edges. So this is basically a data augmentation approach using generative models, and this showed some improvement in all metrics. Okay, that's it. Thank you.